Have you ever played those games where you have to craft everything that exists? Today we're going to do that with planet Earth, crafting everything from atoms to the most complex things we have on the planet. And since we're talking about the universe, let's start by talking about the smallest unit of matter, the atom. It's worth mentioning that nowadays we already know of even smaller units like quarks, but here we're going to stick with the atom for now. It's the basic unit of matter. Everything that exists is made of atoms, and each atom is made up of three main particles: electrons, protons, and neutrons. Protons have a positive charge of +1 and are located right there in the nucleus of the atom. They determine the atomic number of the element. In other words, it's the protons that define which chemical element we have. For example, hydrogen has 1 proton, while helium has 2 protons. And with that, we've already created the elements. By the number of protons, we determine which element will be formed. Also in the nucleus, we have neutrons, which have no electric charge, and their main function is to stabilize the nucleus, preventing the like-charged protons from repelling each other due to their positive charge. Electrons, on the other hand, have a negative charge, -1, and orbit the nucleus in regions called energy levels or shells. They are directly involved in chemical bonds, so the more external they are, the more important they become for forming molecules. In just 1 minute of video, you've already understood that an atom can form different chemical elements simply based on the number of protons it has in its nucleus, and that, in addition, besides having an element that is an atom, it can also bond and form molecules and compounds, such as our table salt. It is the bond between Na, which is sodium, and Cl, which is chlorine. The electrons are arranged in shells, and the outermost of these shells is called the valence shell. And it is this shell and the number of electrons it contains that will determine how this compound bonds with others. And before we go any further, I have to mention that everything in nature seeks stability, aiming for its lowest energy state according to the conditions it is in, including the atoms and elements we've discussed. And to achieve this stability, we have rules that define what will be stable and what will not. So we have the octet rule and the duet rule for the valence shell of these electrons. The octet rule states that we need to have 8 electrons in the valence shell for the element to be stable. And the duet rule refers to having 2 electrons, with some exceptions, of course. Alright, but what determines how many electrons we have in the outermost shell? What determines the electron configuration? So we remember that an element is defined by its number of protons, right? And if it has a certain number of protons, that means it will have the same number of electrons. And these electrons will be distributed among the energy levels, which is basically a division that science created to try to understand how many electrons fit in each shell. For example, the K shell can hold 2 electrons, and we start the distribution there. So taking chlorine as an example, which has 17 protons, that means it will have 17 electrons. And we start by distributing 2 electrons in the K shell, then 8 in the L shell, and after that we only have 7 electrons left to place in the next shell, which means its outermost shell will have 7 electrons instead of 8, as required by the octet rule. And in order to become stable, they will want to give away or receive electrons to complete that shell. What determines whether they donate or receive electrons is how easily this process happens. So in the case of chlorine, it's much easier for it to receive 1 electron than to donate 7, right? Now, for example, in the case of sodium Na, it will have 1 electron in its valence shell, which means it's much easier for it to donate that electron than to gain 7. And that's how bonds are formed, through these valence electrons, and that's why we have our table salt. In the periodic table, the elements are listed by their neutral atom. As we've seen, protons equal electrons. But when they give or gain an electron, they start to be called ions. And they do this because, as we've seen, they are not stable in the state they were in. They need to give or gain that electron. An ion that has lost an electron, like Na, is called a cation, and an ion that has gained an electron is called an anion, like Cl. In less than 5 minutes, we've already created our atoms, elements, the bonds, and understood why they bond together. So things don't just happen out of nowhere. They happen because there are rules in the universe that govern everything that exists. And for all of this to bond, we're going to have different types of bonds. Here, we're going to talk about 2 types, ionic and covalent. So the ionic bond either donates or gains electrons, as we've already seen, and it's a weak bond. On the other hand, the covalent bond is much stronger because they will share the same electron when they have no other alternative. So how does nature determine which type of bond will occur? When we have one atom wanting to donate and another really wanting to receive, as is the case with table salt, an ionic bond occurs. But when the number of electrons in the valence shells is very similar, they will then share electrons to try to stabilize themselves and complete their shells at the same time. And since they are sharing the same electron, they are much closer together, which results in much stronger bonds, like the bond in water. With these bonds, we formed everything we needed in the universe, for example, water. Now then, we need to see how we're going to form our Earth. So the Earth began 4.5 billion years ago from cosmic dust and gas from the solar nebula. These grains of dust we had were made up of atoms and light elements such as hydrogen, helium, carbon, oxygen, silicon, and iron. These atoms combined, forming simple molecules as we have already learned, as well as minerals and solid particles. These atoms and molecules bonded together through gravitational forces and chemical bonds into larger particles called planetesimals, that is, tiny protoplanets. These building blocks began to come together, creating a larger body that would become a prototype of planet Earth. And right after the formation of this protoplanet, the planet was so hot due to meteorite impacts and radioactive decay that its outer layer was a global ocean of magma. But as this planet cooled down, that is, as it lost this heat, gravitational differentiation occurred. The denser elements, like iron and nickel, sank to form the core, while the lighter elements such as silicon, aluminum, calcium, sodium, and potassium floated toward the surface. But if today we know that rocks are recycled and are not always the same, how do we know that the Earth is 4.5 billion years old? This is determined through zircon grains. Zircon is an extremely resistant mineral, able to withstand weathering, erosion, and high temperatures. And the oldest zircon grain that we know of was found in Australia, and it was dated using chemical dating to 4.5 billion years, meaning it is the oldest grain known to exist. So nowadays, we have 46% oxygen in our Earth's crust, which forms bonds with hydrogen. So, for example, they form water, oxides, metals, and this allows for life and chemical reactions, since we breathe this oxygen. The second most abundant element, making up about 28% of the crust, is silicon, and it is the main element in silicate minerals, for example quartz, which is that mineral we love and find beautiful, and it forms strong crystalline networks, giving hardness and stability to these rocks. And then we also have aluminum, iron, calcium, sodium, potassium, and magnesium in other compositions, which together make up what we know today as Earth. And to talk about other things, we have to say that our planet is still alive. It remains alive thanks to the theory of plate tectonics. So the tectonic plate boundaries that we will look at here are zones of interaction in the lithosphere classified according to the movement between plates. So, convergent boundaries occur when two plates collide, divergent boundaries when they move apart, and transform or strike slip boundaries when they slide past each other side by side. I'm not going to go too deep into this here, since we already have a video on the channel about it, which I'll link here, because otherwise this video would be 55 hours long, right guys? But basically, in our mantle, we have rocks that are just a little bit liquid, meaning they have a plastic behavior. That small amount of liquidity already allows us to have convection currents. These convection currents are this liquid moving, which provides the force to move these plates. Wonderful, now we have our Earth fully formed. So we've seen that the elements form minerals, which form the crust, that we have driving forces inside the Earth that move this whole system, which are the convection currents. But do we have any examples of this happening today? And we have answers in the Wilson cycle, which is the cycle that talks about the birth and death of a continent. So for example, Pangaea, Rodinia, all of these were once great continents that eventually became what we know today. Or if we look at the stages of the Wilson cycle, the heat coming from the mantle rises, the continent starts to arch and fracture, and a thermal dome forms there, as we currently see in East Africa. The fractures become a rift valley, meaning the crust begins to separate, and magma continues to rise and create new crust, with the African Rift Valley as an example. Then, as this opening continues, the rift turns into a narrow ocean and oceanic crust begins to form, as we see in the Red Sea. When we have a mature ocean, the ocean keeps expanding, the plates move apart, and new crust is created at the mid-ocean ridge, as in the case of the Atlantic Ocean. But we have to remember that if a plate is moving apart on one side, it will collide on the other side, since the Earth is round, with another plate. In other words, on this other side, the oceanic crust gets older, cools down, and becomes denser. It starts to sink beneath the other plate and the ocean begins to close, as seen at the edges of the Pacific. Subduction is active, volcanic arcs and mountain ranges form, and the ocean then shrinks. Until eventually two continental plates come to meet each other. All that oceanic plate we had created in between has already disappeared. Continental collision is imminent, and we end up generating gigantic mountain ranges, metamorphism, and thickening of this crust, as it accumulates, like in the Himalayas, for example. But if all this is happening, my God, when is it going to end? The complete Wilson cycle takes from 300 to 600 million years, meaning that the entire span of human civilization will occupy only a microscopic fraction of that. We won't see all of this happening in real time. We formed the planet, but as we've seen, it remains alive and the rocks keep recycling. So the rock cycle will describe how any rock can transform into another over this geological timescale. We have three major groups of rocks: igneous, sedimentary, and metamorphic. and none of them is a final stage. They are all temporary stages in the flow. Igneous rocks originate from magma. Sedimentary rocks originate at the surface through sediments from other rocks. And metamorphic rocks originate from the transformation of one rock into another. Igneous rocks are formed from magma. That is, this magma rises, crystallizes, and organizes itself into crystalline structures that will form minerals. They can be intrusive or plutonic, meaning that this magma settles in the crust for some reason that causes it to stop, cooling slowly and forming large crystals, which will create, for example, something we love, granite, which we use in our homes. On the other hand, extrusive rocks, which are volcanic, cool quickly and form small crystals because they don't have time to grow. So these are the rocks that are actually expelled by volcanoes. So the first rocks that formed were igneous rocks. Soon after, we have sedimentary rocks. So as soon as these igneous rocks reach the surface, they are subject to erosion, deposition, compaction, and all these types of weathering they can undergo. The exposed rock will undergo wear, which will generate sediments, in other words, small pieces of those rocks that are carried elsewhere. These can then be compacted by the weight of other rocks and sediments that are deposited on top, eventually forming layers. They can be biogenic, for example, made up of material of organic origin, such as fossiliferous limestones, which are fossils of small ocean animals. And then they can later become metamorphic rocks, which originate from transformation. The rock does not melt, so it's not as if it turns into magma. It transforms while remaining in a solid state. This happens due to pressure, temperature, and chemical fluids, which are hot fluids that pass through there. Where do the pressure and temperature come from? For example, we can talk about subduction zones, that is, where two plates meet, there will be a very strong force, which will end up partially melting these rocks. And it's not a perfect circle, it's a network of pathways. An igneous rock can become a sediment and turn into a sedimentary rock. It can undergo pressure and become metamorphic before turning into sedimentary. It can melt again, become magma, and turn back into an igneous rock. A sedimentary rock can be buried and become metamorphic, or it can erode again and become a new sedimentary rock. So this cycle is not linear. This happens on its own. The driving forces are plate tectonics, the Earth's internal heat, which is partially generated by radioactivity, gravity, climate, water, geological time. But without tectonics, this cycle pretty much stops. And here we have just finished forming our Earth. And I have to say, folks, it took 25 years to edit this video, so if you liked it, go ahead and like it, subscribe to the channel, and share it if you can. Bye bye.